All right, once again, when I am live in the chemistry building, and we'll have a lecture here in a moment, I would first like to solicit questions. If anyone has questions on this file, homework 1, which is due tonight at 11:59 p.m. Okay, if there are no questions on problem set 1, remind you if you didn't attend the lab lecture Tuesday, it means you have a Thursday lab section, and there is a lab meeting at 2 p.m. today. All right, I guess I'll stop sharing homework 1. Beg your pardon. Okay, what we had established last time, and I'm flipping to that place in the lecture handout, is that there are at least 2 instances in which you need, well, ideas about photons in particular and about quantum energy in general to explain stuff that is seen going on. In other words, a couple of things not covered by classical mechanics. All right, I'm on page 11 of the lecture handout at this point. And on this page, let us see. We introduce, or I remind you of, the Bohr theory of the hydrogen atom. And the hydrogen atom emission and absorption spectrum. And you were actually first introduced to this probably in your general chemistry 1 course. All right, the absorption, it turns out, well, this was observed in the solar spectrum versus hydrogen atoms, free hydrogen atoms, not hydrogen molecules, emit and absorb radiation only in specific wavelengths. In other words, if you shine radiation on them, the hydrogen atom absorbs only a certain wavelengths. And the hydrogen atom, once energized, will emit radiation, but that is, again, at the same wavelength. And if you come down to page 11 of the lecture handout, sorry, having a Blackboard issue. you will see Bohr's atomic model, which was used to explain the fact that only certain wavelengths are absorbed and emitted. Okay, let's look at the model in particular, which are these circles halfway down the slide. Okay, to explain the fact that only certain wavelengths are absorbed or emitted, theorist Bohr invented a model of the hydrogen of the atom, with which we're all familiar, which is the hydrogen atom is like a tiny solar system. The nucleus is the sun, and it has, of course, a positive charge. The electron, which has a negative charge, is attracted to it by electrostatic attraction, and hence the electron goes in a circle around the nucleus like a planet goes around a tiny sun. A tiny planet goes around a tiny sun. Bohr's big contribution to this idea was the idea that only certain orbits or certain energies are allowed. If a planet or electron far away from the nucleus is far enough away, it has essentially no energy, no potential energy. And then you have an attractive potential energy as the planet gets closer to, or the electron gets closer to the nucleus, with the result that low orbitals or close orbitals have low energy, and that orbitals at a further distance from the nucleus, orbits at a further distance from the nucleus, orbit or orbital, as you see in the picture, has more energy. So the lowest energy is K in this hypothesis, and then you have another one at L, and then you have another one at M, and you may be more familiar with the idea of numbering these. It's like the first, lowest one would be 1, and then you have 2, and then you have 3, and so on. And now only specific energies are allowed in Hubb's idea. You can have the energy for 1, or you can have the energy for 2, but you can't have any energies between 1 and 2. In other words, the energy of the atom comes in discrete bits or is quantized. The whole thing with the radiation then is that, for example, if an electron jumps from 3 to 2, as in the picture, a photon is emitted, and the energy of the photon is equal to the energy of 3 minus the energy of 2. One of the big ideas of this course in quantum mechanics for chemists is that the energy of whatever photon you may be interested in has an energy equal to the energy difference of 2 states. I summarize that here. This is delta E equals h nu. Remember, this is nu. So if you know the energy of E and the energy of 2, you can calculate a specific frequency or wavelength at which energy is emitted, or if you do the other thing, like exciting from 1 to 2, for example, that corresponds to the energy of a photon or the frequency of a photon absorbed. Okay, I'm going to page 12. Please zoom in on page 12 if you can. Okay, the Rydberg equation, which appeared in 1890. Okay, this equation gives the experimentally observed, hence the word empirical from the source, experimentally observed wavelengths at which atoms are emitted to absorbed. So here in the equation, This is a wavelength at which an H atom emits or absorbs. R is a constant. Appears down below. Note the units of R are reciprocal centimeters, and N's are a pair of numbers. Any whole numbers, 1, 2, 3, 4, 5, 6, etc., with the caveat that the second number must be bigger than the first. The second must be bigger than the first is what makes this come out positive. So if you want to know the wavelength of a photon, it turns out in Bohr theory, corresponding from going from 2 to 3, or 3 to 2 is what we were talking about. Or if you want to know, for example, what happens for the absorption I drew, let's do that. States 1 and 2 of the atom. We stick in the formula. Like so. And you get this number, 3/4 R. And hopefully you also get, like me, 8, 2, 2, 5, 8.2 centimeters to the -1. Okay, you actually probably used this formula as a freshman. And we're going to spend a lot more time talking about hydrogen atoms later in the course. So what we have here is the reciprocal of a wavelength at which light is absorbed. Corresponds to a jump from 1 to 2 in the Bohr theory. Perhaps the most interesting part about it are these 1/centimeter units, which are called wave numbers. You probably had the experience with wave numbers for peak at which light or radiation is absorbed back in organic chemistry and IR spectroscopy. Historical problems with this theory, which worked for great for hydrogen atoms, were it can't deal with more than one electron. Helium, for example, also emits and absorbs at specific frequencies, and Bohr's model couldn't predict or explain the frequencies for the helium atom. And there was a point from classic physics, which is if you have a charged thing going in a circle, because it's under attraction, it is therefore being accelerated. And classical physics predicts it should give off radiation. And hence lose energy, and so that any electron in an orbit around the nucleus would spiral in a circle as it lost energy until it ultimately collided with the nucleus. And in classical physics basically predicts that kind of model of the atom is not stable. So why is the electron stuck in these orbits, which is in fact what makes the atom stable? Okay, Bohr didn't have an answer. On the next page of the handout, lecture 13, guy named DeBroglie had an answer. DeBroglie said, well, light acts like particles. So what an electron is wave-like? Then there must be an integral number of electron wavelengths per orbit circumference. In other words, if the electron is going around the nucleus in a circular orbit, there must be a whole number of waves in the orbit. That ensures when you get around to where the circle started, at the beginning of the wave matches up at the end. Okay, so he says, well, there must be an integral number of wavelengths per orbit circumference. How can I figure out something about waves of electrons? Okay, relativity, again, Einstein had just figured out this formula, E squared equals PC squared plus MC squared squared. Now, if the momentum of an object is 0, this equation produces everybody's favorite relativity equation, which I'm sure you've all seen somewhere. E equals mc squared. P, let me remind you, because it will come up again. Is a symbol for momentum from physics. If, however, m is 0, as the case of a photon, E is PC. Since we already knew E is h2 or hc over lambda, hc over lambda must be PC, which leads us to P equals h over lambda. In other words, the momentum of a photon is predicted, which is inversely proportional to its wavelength, or directly proportional to its frequency. Okay, this is frequency because a photon supposedly has a mass of 0. But turns out photons have momentum, and one of the things that explains is laser cooling. Imagine a situation in which an atom is moving in this direction pretty quick. Okay, because it's moving pretty quick, we'll call it a hot atom, because you know from last semester that hot atoms, well, hot means particles move fast. You irradiate it with a photon of a certain wavelength from the opposite direction. If the atom absorbs the photon, the atom receives a kick in the opposite direction with momentum equal to the momentum of the photon. The atom emits radiation later because it's been excited, and on average, well, that can go in any direction. So on average, the atom's momentum or speed is reduced by half. So the atom has been cooled by the radiation from the laser. Hit an atom with enough photons and you can bring it to a stop. And that is the whole idea behind quote unquote laser cooling. Okay, so the momentum of a photon is a thing. It's a really real thing that actually gets used in various physics or chemistry experiments. Well, if you believe that lambda equals h over p is some sort of rule in general, and you remember that p is mv from physics, you could write down this formula about wavelength for anything with mass. So this, in principle, should apply to all particles with mass. And you could apply it to an electron, for example. And when you apply it to an electron in a hydrogen atom, you find whoops, I should go back. You find down at the bottom of the overhead that it predicts that electrons in the Bohr atom have wavelengths or I should say that they have orbits with have a circumference that atom has circumference equal to a multiple of DeBroglie wavelength, in particular a whole number multiple of DeBroglie wavelengths. In other words, this theory worked for the hydrogen atom. All right, let's look at this blank page for a minute. There are some things to talk about with the DeBroglie theory. Not new, V. I'm getting messages from Collaborate. Can everyone see? Okay, good. All right, let's think about this equation for a second. This is supposed to apply to any chunk of matter which may happen to be moving around. So electrons, for example, and it can be applied to electrons. There are equations with electron diffraction that look just like the double slit experiment for light. If you've looked at homework, beams of neutrons can diffract like waves. And that's a way of determining where the atoms are in crystals. But other things aren't wavy. Suppose that a car weighing around 2 tons is going around 30 miles an hour. Why doesn't it look wavy? And anybody who drove in anywhere this morning, you know, presumably watched cars going down the road. They don't look wavy. Never mind what it would mean for, you know, an electron or a neutron to be wavy. But there's too much, well, you know, nothing wavy about your car. Why don't we worry about DeBroglie wavelengths in everyday life? Increasing the mass, Aya has it, makes the wavelength really small. It's not the speed as such. In fact, there's a v in the denominator. The slower the thing is, in principle, the longer the wavelength will be. But h is around 7 times 10 to the negative 34 to one significant figure. If you have a normal mass of 2 tons, which is, for example, close to 1,000 kilograms, at a reasonable speed, 30 miles per hour, some multiple, a few hundred meters in a second. This thing is going to be incredibly tiny. 10 to the negative 34 or less. So molar scale objects, pretty much this is something that the DeBroglie wavelength is something you never think about. It's a rule of thumb that's useful for thinking about wavelengths of microscopic objects, except for note the funny part where it blows up if the object's not moving. So the Broglie wavelength is the best you will see. Well, a recurring formula that pops up in some cases. It's sort of a rule of thumb about what waves of matter are like. All right, are there questions at this point? Okay, I will say before we leave this lecture handout and move on further in Unit 1, that this is another place which offers an opportunity to mix up the and new. In this formula, we have a V not to be confused with a nu. All right, I stopped sharing this lecture handout. And we'll move into lecture handout 2. Okay. First page is source material. It's hopefully fairly obvious what the source material is about. Eigenfunctions and eigenvalues, for example. You'll know what those are about here momentarily. This points at important equations I'll talk about today. Other information in here is sort of organized by topic. You will refer to it later when doing problems. Let me move on. Okay. So we have the idea of these wavy electrons now. Except we all know that an electron, well, according to the Bohr theory, is a tiny rock. In what sense can an electron, or any chunk of matter, be wavy? Okay. First in all these formulas, something that comes up, this is kind of mundane, but it's kind of important. H bar, or H with a bar through it, is H over 2 pi, and that number is right here. I do this because this constant will come up a lot in your calculations. Okay, it turns out that any system of matter has some sort of wave function, which is about it's a mathematical function based on the position of where things are in the system. And you can write an equation for the wave function of any material thing. Looks like this. I should have H bar over I in parentheses. Okay. Yeah, there's a lot of weird stuff going on in this equation. The first thing I want to point at is this I thing, which is I is the square root -1. Okay. I'm really not asking you to understand much more about this thing at this point. We'll come back to it later. Except note, in this thing, there is a term that talks about how the wave function changes with time, which things in this equation this equation is good for things that move around as time goes on. We're not going to worry about that right now. Chemists are often interested in situations in which things are standing more or less still. We're going to talk about that most of the time. Okay, so this function, which changes with time, must be a function of position and time. Here it's a one-dimension possibility, and if you can imagine a one-dimensional object, the coordinates would be x and t. A 3D object, like, you know, an electron in space would have coordinates x, y, z, and t. Or if you have two electrons, for example, or an electron and nucleus, you would have x1, y1, and z1 for wherever the first thing is, and x2, y2, and z2 for wherever the second thing is, and then t for the time variable. Right. Life gets a lot easier if things are time independent. In that case, this wave function, which here I'm using 1D for an example, can be separated into a function about position and a function about time, and you could show the function of time behaves like this. That is, it's an exponential function of I. I want to come back to this. In a bit. basically, if we don't have to worry about time, and there's a reason we're going to be able to ignore this, I'll come back to it in a bit. All we need to think about is this position function if things are not moving with time. That brings us to the primary equation we're going to look at in this course, page 3 of what your handout 2 up at the top. The time-independent Schrodinger equation. Right. This supposedly can be used to describe any system which is more or less standing still in time. For example, an atom floating by itself in space, for example, you'll see. Okay, first there is a wave function, which is the thing that makes matter wavy. This is a function of the variables of position, as we see. The wave function appears, here on the right-hand side, multiplied by energy, which is a constant, and I'll explain what eigenvalue is in a minute. It's an eigenvalue of the Hamiltonian operator. What eigenvalue means is, well, here it is again on the left-hand side, the wave function. It is operated on by an operator, which is a thing that turns a function into another function. The Hamiltonian operator in general is the operator for the energy. Okay, I know there are a lot of confusing parts here. The fact is, this is an online lecture, doesn't help a lot. Let us first, here's some stuff on operators. Let's skip the part with the operators for a second and come to the part where we talk about the wave functions, which is on page 6. Okay. As we've seen, well, from the eyes that have already popped up in here, wave functions are themselves sometimes complex. Okay, I have prepared a link with some information you need to know about complex numbers here. Please see complex numbers, complex conjugate, and absolute value. I'll talk about those now. A complex number, well, you all know that there are real numbers now and imaginary numbers multiplied by I. Any complex number can be written A plus B I. Okay, A is the quote-unquote real part. It's a real number or function. It can be a function. B is also itself a real number or function. But it becomes imaginary because it is multiplied by I. Okay, so you can show it is true. There are any complex number can be made to look something like A plus BI. Any complex number has a complex conjugate. Now you will need to know that the way to make a complex conjugate, sorry about that. to make a conjugate, replace I with negative I. In other words, for any complex number, a plus bi, there is a conjugate a minus bi. Okay, now if we're talking about a function, well, all right, let me erase the board. If you have a complex function f, it can be written in the form a plus bi. Likewise, you know there is always a conjugate, which can be written a minus bi, and we'll call that f star. Star meaning complex conjugate in general. Okay, note that if you take f times f star you're actually multiplying a plus bi times a minus bi you have something a squared plus abi minus abi minus b squared I squared, and since I squared is -1, this is simply a squared plus b squared. So anytime you multiply a complex number by its conjugate, you will get a real positive number. Okay, these wave functions give probability distributions. By give, I mean the probability distribution for the particle, whatever it is given by psi, which is what we generally call the wave function, times psi star. And psi times psi star, the wave function times its complex conjugate, is a probability distribution function. Okay, now life gets really easy if psi is not complex and it's just real. Psi star psi, since there's no I to replace with negative psi, if psi is real. And then say if psi is real, psi star equals probability distribution function. Okay, so suppose this is the x-axis and I'll plot psi on the y-axis. Looking at this figure here I've drawn on the right-hand side. Suppose psi looks something like this. Well, then as you imagine, psi squared has to look something like this. Okay, you had probability distribution functions last semester. And this works pretty much the same way, where there's a peak or the function is large. That's where the probability is high. So this means that this is where the probability of finding the particle is high. Where psi squared is small, the probability of finding the function is low. Okay, because now I'm on the second page, I'm going to talk about, whoops, normalization now. Of the way, because of the way psi is defined, we need to worry about something called normalization. In other words, since psi star psi is a probability distribution function, if you integrate over all positions, and psi is about probability of position, supposedly. If you integrate over all the positions, you're supposed to get a 1. In addition, there's a property called orthogonality. Anytime you write h psi over e psi for any system, for any energy operator, you will always find for any Schrodinger equation. What orthogonality means, first, this means by itself, there's a psi 1 with d1, and a psi 2 with e2, and etc., and so on. If I take the complex conjugate of 1, multiply it by 2, integrate over all positions, I will get a 0. That's true anytime it's two different functions. So if I take complex conjugate of psi 2, multiply it by psi 3, integrate all over the positions, I'll get a 0, and so on. Further property is, well, okay, let me jump away from here and we'll go back. Page 4 of the handout, zoom in, and we'll talk about what's an operator. Okay, in quantum mechanics, any physical observable has an operator. All right, I need to talk about operators. Tell you what, let's go to the whiteboard for a moment. No, I can't share blank whiteboard. Hi, everybody. It looks like I can't share whiteboard. And I'm trying to get Blackboard to let me share files again. And I can't do that either. Okay, so I guess I'm going to stop